Hello everyone, welcome to this session. In the previous session we discussed the charge pump design, and now we also discussed the reasons for mismatch in the current output for the charge pump, and then because of this mismatch how it will lead to the whisper at the output of the oscillator. So, in this session we will look at how to address these mismatches. Okay. So, we are going to talk about the methods to address these mismatches in source switched charge pump, okay, which is quite commonly used. So, previously you had seen that there is a current mismatch between the charge pump and between the up and down current sources. Okay. So, this is what we used earlier, which this is a bar, this is down, and you have this is VBP. It was generated using a replica biasing scheme, and because of the channel length modulation, you will see that this particular current source has mismatch. Okay, voltage is this and ICP. The current which is flowing here is I up, and the current which flows here is I down. The way we get these voltages was something like this. So, I will just copy it. This is what we had earlier. Okay, this was 0 and this particular thing was VDD. Okay, and then you can have copy. Okay, fine. Okay, so we can remove this and have a current source, an external current source like this. This is connected here, this, and this is done in this manner. Okay, this is connected here. So, this is how we actually designed our bias for the charge pump. This is current I naught. The current in this branch will be I 1. Depending on the matching between the second branch and the first branch, you are going to see current I 1 equal to I naught or with some mismatch. And then when you have a in the actual charge pump, you have a control voltage. So, because of this control voltage, you will see a mismatch between the current ICP and your I naught. Okay. Now, in order to increase the matching or reduce this mismatch, what we can do is we can have a cascaded current source that will be lesser susceptibility towards your V control. So, what I can do is the following. So, I have V control your up MOSFET, and then I have a cascaded PMOS current source, okay, like this. Similarly, cascaded NMOS current source, and these two cascade voltages are going to be generated using replica biasing scheme. So, this is still a bar and this is down. The output of the charge pump is this, going to a loop filter with a control voltage V control. This is VBP1, VBP2. Similarly, you have VBN1 and VBN2. These 4 voltages are generated using the replica bias scheme. Okay. Now, whether you are going to use some kind of diode connection or using amplifiers, that depends, but the thing is that in this particular case your actual current source, if you look at it, you have the current source here and this particular current source. Okay. Assuming that the top MOSFET and bottom MOSFET, they offer only a very low amount of resistance and they are operating in the linear region. Both these all these 4 MOSFETs are operating in saturation region. So, the susceptibility of the current or the variation in the current due to V control is going to be minimum, because you will maintain same VDS when it operates as compared in the bias case as compared to the charge pump. So, if I just take this branch and start generating these bias voltages. So, let us say I have it here. So, all this go away, right, and for example, I am going to generate the bias voltage. This is going to be 0 and you will keep this. So, okay, one of the methods can be, you can do this. And then this particular is passed on, this is 0, right. You can have the same current I naught here and generate this VBP1 and VBP2. Okay. The size of this particular MOSFET will be chosen independently such that you get the desired VST across this PMOS transistor. So, in this way you can generate. Now, if this is the main current source, what you will see is in the regular operation the VST of the main current source remains roughly the same even when V control varies. So, VST for the Cascade transistor will vary, but not the actual current source. So, the current will roughly remain the same. Similarly, you can generate the bias voltage for NMOS also. So, this way it helps in reducing the static mismatch. Okay. So, with cascaded currents, cascaded current sources, static mismatch is reduced. Okay, but this has a problem that your V control range reduces. V control range reduces. Okay, and by the way, when you have the cascaded PMOS, both these PMOS should operate in saturation region. That is the reason that V control range reduces. In the presence of cascade, your actual parasitics will also increase. So, the switching of the current sources slows down. There is a trade off. Okay, it is not that it comes on its own with no trade off, slows down. Okay. Now, other thing is that V control varies all the time, and this particular method has the problem of your speed, okay, and your range for V control. So, there is another method which helps in reducing the current mismatch, and let us look at that architecture with some improved dynamic current matching. Okay. When V control varies, even in the presence of varying V control, we can get the proper matching. So, the basic idea is the following, that you take this actual charge pump, source switch charge pump here. Okay. Now, one thing is that your V control voltage varies all the time. So, with respect to if V control varies, we have to decide the other bias voltage or the current source accordingly. Okay. So, here what we can do is we can have the same we can have the current bias generation for NMOS like this, where this is VDD and you force in the current source, get this VBN. Okay. Now, this VBN is passed to another NMOS transistor. So, you have this current, if this current is I naught, you are forcing that this current is also equal to I naught ideally, okay. And then the PMOS current, which earlier you were deciding with the diode connection, now that PMOS current you are going to decide based on the control voltage, okay. So, this PMOS current, which is finally going to be actually connected to VBP, this is going to be decided based on the V control voltage. So, the method to do that is that you tap this V control voltage, okay, buffer it, and in the current biasing branch itself you try to force this voltage also as V control. So, if I call this voltage as V CP, okay, VC charge pump biasing, then this VCP biasing should be equal to V control in the regular operation. So, what will happen is if I want to force it, what I need to do is I need to compare this voltage, whatever your buffered V control voltage, with our buffered V control voltage. So, I will take this V control buffered V control voltage connected here, and then I choose the V bias voltage. Okay. So, here what is going to happen is, just think about it, that you may bias your charge pump with V control. If this is VDD, for example 1.8 volt, you bias your charge, your loop filter is at 0.8 volt for example. Then what it is going to do is, this biasing is going to do, it is going to find the VBP voltage in such a way that VCPB is also equal to 0.8 volt. Okay. So, in the regular operation of the charge pump, you will have it will not be like that you are having a different VDS voltage, because of which you have a current mismatch. So, let us say if this is I naught here and this current happens to be I 1, there may be some mismatch between I naught and I 1, whatever that mismatch is, that is fine. Now, I am choosing the bias voltage of the PMOS in such a way that the VSD of the PMOS is in the regular operation close to VDD minus V control, and VDS of NMOS is also equal to V control. So, your I up current will be equal to I 1 and I down current will be equal to I 1. Okay. Then the rest is the mismatch between these two transistors, but whatever you will have because of different V control, the 0.8 volt you can go up to, let us say 1.4 volt, and you go up to 0.4 volt at the bottom, right. If you have even this variation, you will change the bias voltage here. Okay. So, in this way you can take out or you can suppress your dynamic mismatch between top and bottom current sources to a great extent, right. Now, you see here that you want to look at the feedback loop. So, if V control voltage is higher, right, if V control voltage increases, here this voltage increases. If this voltage increases based on the amplifier here, this voltage drops. If this voltage drops, then VCPB increases. It will become equal to this only. Okay. Now, in this case, what you see is during the regular operation of the charge pump, you will have some current which is flowing into the loop filter, right. What we want is that there is a matching between I up and I down. So, there should be minimum mismatch between I up and I down because of the V control voltage. So, it will try to do that, but whatever happens, whenever you are adding any current to V control, we have seen that in the presence of the loop filter, your ICP will create a jump in the control voltage. Okay. And when it creates a jump in the control voltage, you can say that this particular, you see any change in the control voltage, this particular loop gets activated, okay, and well, it is changing VB here. So, it seems like for example, if we control voltage increases in a steady state, every reference cycle you have some current which is added to the loop filter. So, if we control voltage increases, what this particular loop is doing is if this voltage increases, it is trying to this particular loop also acts and it responds to local disturbance. Okay. What we want here is that during the regular operation of the PLL, we control voltage changes for the desired output frequency. So, for different output frequencies, whatever your control voltage is, right, with respect to that control voltage, I should bias my I up and I down in such a way that there is minimum mismatch. But the charge pump, this control loop starts acting on every reference cycle, which is something which is not needed, and it can create problems also if it is not stabilized properly. Okay. So, what we need to do is we need to stabilize this loop, this particular loop with the help of a Miller capacitor here in general, okay, and the bandwidth of this loop can be quite less. Even then what you are going to see, there will be some disturbances which will come for in order to minimize the disturbances on which the loop acts. In place of directly taking the V control from there, so ideally we know that this particular current is actually going to the loop filter with R and C1 and C2. Okay. So, your V control voltage and your VC voltage across the C1 capacitor, the DC value of these two voltages is the same and it will change only when you require the oscillator's frequency to vary. Okay. So, that is the only thing. So, what we can do is in place of having the reference coming from V control, we can remove this and we can actually take the reference from here. Okay. So, the regular disturbances at your V control, that you every time you have a reference clock, you may have some kind of current. These regular disturbances are actually suppressed at VC1 node. So, your this particular loop will not be acting on the frequent disturbances, okay, and this helps in the minimizing the ripple on the V control also, or this helps in minimizing the disturbances because of the PLL and because of this loop itself. Okay. So, in this way we can minimize the dynamic mismatch between your I up and I down. Okay. I up and I down, this is the way which we can use. Now, even after doing all these things, what happens is, well, this works pretty good, but what will happen is that if you look at it, these two transistors which are MP1 and MN1, these two transistors, they go into cutoff and then they go to saturation. So, whenever you have a current source which is in cutoff and then during the transient it goes into saturation, there is some lag, time lag, and even it is not only the simple time lag, the current changes from 0 to the final value non-linearly. Okay. So, that is one problem, and the switching speed is also a problem, that your current source turns off and then it goes to saturation. So, how fast you can switch it is the speed is going to be limited. So, you may not be able to operate this particular charge pump at a higher speed. So, what we can do is in place of switching the current sources in this manner, what we can do is we can keep a fixed current and we can switch the current at the output as desired. Okay. So, normally we call that as a current switched charge pump. Okay. So, here what we do, we have a fixed current value which we generate using the bias voltage, which we generate using some replica biasing scheme, and then this current is fixed, always it will be there, and you switch it to the output depending on your PFT outputs, and this current at the bottom also the current is fixed. So, I generate VBP and VBN in such a way that these two current sources are same. Okay. So, this I can call I up, which is coming, and I down. If these are current sources, then I should have I up equal to I down when I am going to generate VBP and VBN. Then you have other two switches which actually divert the current when the current is not in use. So, if this is up bar, you have up signal here, and for the NMOS case on the other side, this is down bar and this is down. This output is fed to the loop filter. Okay. So, now you see when up bar is equal to 0 and down is up bar is equal to 0, that is like up equal to 1 and down equal to 0. In that particular case, all the up current flows through the switch and goes to the output, and the NMOS current, because down is equal to 0, NMOS current takes this path. Okay. On the other hand, when you have down as 1 and up bar as 1, at that time the current down current flows like this and your up current gets diverted and it goes here. Okay. So, you see that these two MOSFETs, the current source is not switched off at any given time, it is just switched from one direction, or you can say one MOSFET to the other. So, this is quite fast, that you, because your current source is not getting switched from off state to on state. This particular design has a problem that the switches which are operating, these two switches are actually having a V control at the output, whereas when you divert the current to the other direction, the one is ground, other is VDD. So, because of this, the exact current mirroring will not happen, or you will see additional current flowing in the charge pump output. Okay. So, to minimize that, what we can do is, so what we would like to do is the similar thing which we did earlier, that we first, in place of having a different voltage for these switches, we can keep the same voltage as it exists in the charge pump output. So, to do that, we are going to connect it like this, and then what you can do is you can have a buffer which using an amplifier, right, and it connects it here. So, whatever your V control is, you will have a similar V control here. Any mismatch during the current transition will be supplied by the op amp here. Okay. So, in this way you have current sources which are not switched from off state to on state. The current is actually steered from one direction to the other direction, right. And the other thing is that the switches which are steering the current from one direction to the other direction, those switches are also operating with same source to drain voltage, okay, source to drain or drain to source voltage. Now, here also you will see that some kind of, if there is any ripple here, this ripple is also going to change or it will create a ripple at this node. You can get rid of it if you take the reference in the manner as I have taken here. Okay. So, this is one of the fastest method to switch the current in the charge pump. Okay. Now, one important thing is that all this source switch charge pump, this particular charge pump is consuming only during the time when up and down pulses are high, and we know that in a steady state these switches charge pump is turned on only during the overlap period when you have up and down pulses both high. So, the current is consumed in the charge pump, source switched charge pump only when you have the phase error or only during the overlap time, which is much lesser than the reference time, clock period. Okay. But what happens here is, in this kind of charge pump, you are consuming the current always. Okay. So, if you are trying to minimize the power consumption in the PLL, and charge pump current has a significant role to play, right, or significant value is there for the charge pump current, then using source switch charge pump is a less power hungry design as compared to current switched charge pump. Okay. So, that is one reason why you directly do not go for the current switch charge pump unless the speed is a problem or the variation in the small mismatch in the current is a problem. Okay. So, that is what we do. And now current switch charge pump, if you start giving big pulses like 0 to VDD, 0 and VDD, right. So, when you have 0 and VDD, similar things will happen, that this, if you think recall, this is like a drain switched charge pump, right. Yes, because you want to keep the current constant. So, this transistor is always on, you are switching at the drain. So, you get a good amount of clock feed through coming in. Now, this clock feed through is surely a problem. So, we can minimize this clock feed through by not switching these transistors, the switches which you are seeing here highlighted or checked with red, by not switching these switches with full scale signals like 0 to VDD. We can limit the signal which are used for these switches. So, if you think about it, I will just draw the PMOS as a switch. So, this voltage will surely be something, in an ideal case, it will surely be VDD minus VD sat of PMOS transistor. Okay, in a mod I will put it. Now, in order to switch this transistor, the current, if I want to steer the current, I do not need this voltage to go to 0. Okay. If I, and one time it is going to 0 and other time it is going to VDD. By the way, I never want this voltage to go to VDD, because this particular transistor turns off even before the gate voltage goes to VDD, right. So, I can limit the swing for this transistor between some values, okay, depending on our design, and if these two switching values, they are not 0 and VDD, then the clock feed through which is coming through the capacitor, that will be minimized. And similarly, it will similar thing will happen for NMOS also. To turn off the NMOS, you do not need this particular voltage to go to 0. So, your lower swing is limited. On the higher side also, how much swing you need, it depends on the switch size. So, based on the limited swing here, you can minimize the clock feed through this transistor also. Okay. So, as I told earlier that the drain switch charge pump is also used, but quite often in this manner. And if we recall regarding this clock feed through problem, we have to address it by not using full swing for switching the current. Okay. So, no matter whichever charge pump you use, right, what happens is that you have this loop filter, by the way, whatever charge pump you are using. Now, you know the charge pump consists of your MOS transistors, and even when the MOS transistors are off, during the off state also, right, there will be some leakage current. Okay. Some leakage current, I call that as I leakage during off state. Okay. So, what happens is, whether it is draining the charge or it is pushing the charge to the loop, in the loop filter, it depends on the subthreshold current. For example, when if you take this particular charge pump, so the switch is off, right. This one, there is some subthreshold current which is, both these switches will be, both this switch and the current source will be having. Similarly, you have a subthreshold current for this, whatever the error in the subthreshold current between the top and the bottom branch, that will flow as I leakage. And if you have a leakage current during a long, in a steady state, we know charge pump is active only for a small amount of time. So, most of the time the charge pump is off. So, it is like your up and down pulses will be, though this is still a magnified version, during all this time the charge pump is off. Okay, this is your whole time period. This is only T overlap. So, during the off state, you have leakage current. Because of that leakage current, your control voltage changes, and if your control voltage changes in a steady state, your PLL feedback loop will get into action and try to fix it by creating an offset at the input of the PFT. Okay. So, that is what is going to happen. Then the last thing about this charge pump is, as you see that the charge pump gets active only during the time when you have up and down pulses, both are high, right. So, in that case, the noise from this charge pump, so I will let us draw this. So, this is the charge pump which I have, fine, right. So, we know that our up and down pulses in a steady state, they will have some overlap region. Okay. During the overlap region, these two current sources are active, or you can say both the branches are active. Now, when both the branches are active, then the noise current, whatever the noise current you have, the difference in the noise current is going to flow and come at the output. We have seen this earlier, this is just now with the transistors. So, if I call this as thinking or assuming that the current sources are going to dominate the noise, I call this as INP and this is INN. So, the noise current is going to be present only during the time when both the switches are on, and the difference of the noise current is going to flow, but these two currents are not correlated. So, what you will see is that the charge pump noise spectral density, okay, is going to be T overlap by your reference clock period. I am just writing R as a subscript to denote that this is reference clock period times, you can say, the current density for the PMOS as PMOS of F, noise spectral density for the current source, and this is NMOS. Okay. This is what we have seen earlier. Okay. So, that is how the noise will come from the charge pump. An important part here is the following, that it is not only the noise contributed by this transistor. Okay. So, whatever noise you have because of this transistor and this particular transistor, these two noise sources are going to change the VBP voltage here. Okay. Similarly, the noise of this current source is going to change VBN here. Okay. So, I will call this as IN0, this is IN1 and this is IP0. So, because of IN0, because of noise in the bias transistors, VBN and VBP, here I am assuming the amplifier is ideal, but you can think because of the amplifier noise also, VN and VBP will have noise Why it happens? Because when you have a noise voltage here, it will change the VBN voltage. It is going to change. Similarly, you will change from IP0 and IN1, it is going to change. How to find how much contribution? Well, that is easy. Let us say you consider the first bias branch. So, first switch I am modeling as a resistance, though it also has a noise. Then I have the current source. Okay. So, you draw the small signal model, and after drawing the small signal model, you can very well find the voltage and noise contributions. Okay. So, with the help of a small signal model, you can find what is this VBP voltage. Now, if VBP voltage is noisy, then based on the GM of this transistor and the GM of NMOS transistor, that noise also gets amplified at the charge pump output. Okay. So, the idea is that this noise which you are seeing in the parenthesis, this noise is not only due to the transistors which are present in the final charge pump, but the noise is also due to the bias branches which are contributing noise at these bias voltages. Okay. It is quite important, it is not rejected. Okay. So, you cannot say that okay, you have simulated the noise only for this branch, because this is the main charge pump, and if it contributes some noise, I will take that and I will discard the bias. The reason why this is very important, quite often what we do is, if we want a current of 1 milliampere, we do not like to burn 1 milliampere current in the bias branch. We may burn only, let us say, 100 microampere here and 100 microampere here. Okay. So, from power consumption point of view, the bias is consuming much lesser power than the actual charge pump required. What happens in the actual charge pump current requirement? This charge pump current is dictated by, if you remember, the loop gain analysis and the noise analysis. Okay. So, this is the number which you will get from your analysis. Bias you will just add to support the actual circuit, charge pump circuit. If you have a less current here, your VBP and VBN are going to be noisy, and when they are noisy, you will have a final output noise also quite large. So, the scaling cannot be skewed by a lot of margin. Okay. You can have 1:6, 1:8, 1:, do not think that you can have 1:1000 scaling and everything will work fine, it does not. Okay. Other thing which you can do is that you have a noise at this VBP, you can add a capacitor at this node to filter out the noise at VBP. Similarly, you can add a decoupling capacitor at VBN to filter out the noise at VBN. So, these two things are utilized to reduce the noise contribution from the bias, but there is also a limit to it, how much capacitor you can add and how much is the noise contribution coming from the bias circuit. Okay. These are all design dependent. You will understand or learn more when you are going to design on your own. Okay. Thank you.